Hi folks, today we'll be talking about combinations, so let's go ahead and get started with a couple of problems trying to distinguish the differences between the two. So we want to determine the number of ways we could select the president, vice president, secretary, and treasurer from a group of 6 people. And if you saw this on the permutations, it should be familiar. If not, we're basically going to use a 4 permutation on a set of 6 elements. And so this is this P64, and so that should equal 6 factorial over the quantity 6 minus 4 factorial, which is the same thing as 6 factorial over 2 factorial, which we could write the 6 factorial as 6 times 5 times 4 times 3 times 2 factorial, divided by our 2 factorial, and our 2 factorials cancel and give us 6 times 5 times 4 times 3, which is 360. So hopefully that's a little bit more familiar to us at this point in time. But how does that differ from the problem below, where we have determined the number of ways we could select a 4-person committee from a group of 6 people? Well, the key difference between these two, if you notice you had that president, vice president, secretary, and treasurer, that has some sort of rank, meaning order is important. In the second case, order is not important. So we may start with this P64, so our permutation where we're taking 4 from a set of 6 elements, but we need to account for something that doesn't have order matter. So we're going to divide that out in a second. And the thing we're going to divide out is the number of ways to order 4 people, because those are being counted multiple times, whereas we don't care on the order. So if we called those 4 people that we're ordering, let's say Al, Brian, Cy, and Di, we'll shorten that by A, B, C, D. So let's see how many ways we can actually write out A, B, C, D in different orders. So you can do this real quick, and we end up getting a whole set of 24 different ways. And you can see them listed right here. But an easier way for us to have done that is actually just write that as 4 factorial. It's the number of ways to order 4 people. That should be 4 times 3 times 2 times 1. So basically, we're going to take our 4 permutation on 6 elements and divide by 4 factorial, which gives us, we found from the previous part, it's 6 times 5 times 4 times 3 in the numerator, divided by 4 times 3 times 2 times 1. And there's some easy canceling that goes on right away, the 4 times 3, and then we can take the 2, and that cancels off with a 6, leaving us with 3 times 5, and that's 15 for our answer. But this order not being important, leads to a bigger sort of theorem, or definition I should say, and that's the idea of a K combination. So a K combination from a set of n elements is just a subset of K distinct elements from that set of n elements, and we denote this number of K combinations by this n choose K right here. And you can also see the Cn K happen every now and then, but mostly we'll use the n choose K. And so what happens then is you get the formula to be given by n choose K equals the number of K permutations on a set of n elements divided by K factorial. Or more simply, we can write this as n choose K equals n factorial divided by the quantity n minus K factorial divided in the denominator as well, K factorial. So in terms of an example here, we'll take a look at what 5 choose 3 equals, and immediately we can plug it into our formula, get 5 factorial over 5 minus 3, that quantity factorial, and then another 3 factorial in the denominator. So this makes 5 times 4 times 3 factorial divided by 2 factorial and another 3 factorial appearing in the denominator. And you'll notice that those 3 factorials cancel, and we're left with 5 times 4 divided by 2, which is equal to 10. So in the big picture, what's actually happening here is that you have a set, let's say, of 5 elements, A, B, C, D, E. If we were to list the 3 element subsets, then this becomes 10 different subsets, and we have them listed out here. And so you'll notice that these two things match, and that's what we're trying to do all the time, is just list subsets of a set, the number of subsets of a set, and we can use that to tackle other problems. So let's take a look at the following example. Determine the number of different 7-card poker hands from a standard deck of 52 cards. When taking a look at this problem, it's best to just kind of consider what's happening. So let's list out, say, 7 cards. How would a poker hand look? And let's say we have Ace of Clubs, King of Hearts, Jack of Diamonds, 2 of Diamonds, 5 of Spades, Queen of Diamonds, and the 10 of Hearts as our cards. Now, if you look at this, it didn't matter what order they came in. That's going to be your hand to play. So with that in mind, what we actually have here is that order is not important whatsoever in this problem. With order not being important, that means we are using a combination. So we can write this as 52 choose 7, which is the same thing as 52 factorial over 52 minus 7, that quantity factorial, and then 7 factorial, which we can write the numerator as 52 times 51 times 50 times 49 times 48 times 47 times 46 times 45 factorial, and then we have in the denominator the 45 factorial and a 7 factorial. And if you notice, those 45 factorials cancel off right away. And that's why we stopped at the 45 factorial in the numerator. So this means that we can rewrite this problem as 52 times 51 times 50 times 49 times 48 times 47 times 46, all divided by 7 times 6 times 5 times 4 times 3 times 2 times 1, which means we can actually start canceling things out. And so we'll begin with the 5 going into 50. That's the easiest one to detect. So that leaves you with 10 on top where the 50 once was. The 2, 4, and 6 should cancel off with the 48. And then the 7 will go into the 49 in the numerator. That leaves us with 7 there. And then finally, the 3 goes into, let's look, 51, and that leaves us with 17 up in that numerator. So our final product is technically just 52 times 17 times 10 times 7 times 47 times 46. And if you take a look, just plug that into a calculator, or you can do it in your head. You get 133,784,560 different poker hands that you can be playing. And keeping that in mind, this is how you basically distinguish between is order important or is order not important for the future problems. So permutations, combinations, distinguishing between those two is the really tricky part, but now we're ready to practice some of those problems.